Hello everyone, my name is Dr. Paul Kerstetter, and today I'd like to talk about reset strategies in the context of FPGA design. In this discussion, I will give examples both in Verilog and VHDL. Correctly implementing a reset can make the difference between a design that works reliably and one that doesn't. FPGA D flip-flop reset solutions with VHDL and Verilog examples. At its core, a reset sets all storage elements, like flip-flops, to a known state before normal operation begins. It provides initial conditions for the FPGA digital system. For example, let's consider a simple example, a traffic light that toggles between red and green, based on a timer. Suppose the light should be red for the first 5 minutes and green for the next 10 minutes. You could implement this using a state machine with a single flip-flop. When the minute counter is less than 5, the state is 0, or red. When the counter reaches 5 or more, the state becomes 1, or green. After 15 minutes, the timer wraps around to 0 and the cycle restarts. Now what happens if we don't initialize the state machine to start in the red state, or 0? It might still work, but there's a risk it starts in the green state instead, potentially causing incorrect behavior. In a real traffic system, that mistake could cause an accident. There are two main types of resets used in digital designs. One, asynchronous reset. The reset signal immediately resets the flip-flop independent of the clock. This type of reset is ideal when fast response is critical, such as during power-up or in fault recovery. Number two, synchronous reset. The reset signal is sampled on the clock edge. The flip-flop only resets when both the clock edge occurs and the reset is asserted. Here is an example of VHDL coded asynchronous reset. Note that the reset signal is in the sensitivity list. Here is an example of Verilog coded asynchronous reset. Note that the reset signal is in the sensitivity list as well. Here is the RTL schematic symbol for both of the Verilog and VHDL codes for the D flip-flop with asynchronous reset. Notice the async in the name. This is a schematic after the Verilog or VHDL code has been synthesized. It is a D flip-flop with clock enable and asynchronous clear. Here is an example of a D flip-flop with synchronous reset written in VHDL. Notice reset is not in the sensitivity list. Here is an example of a D flip-flop with synchronous reset written in Verilog. Again, notice the reset is not in the sensitivity list. Here is the RTL schematic symbol for the D flip-flop with synchronous reset from the VHDL and Verilog code. Note the sync in the name. One of the key issues with asynchronous resets is that if the reset is deasserted near a clock edge, it can violate the setup and hold timing of a flip-flop. This can lead to metastability. Metastability occurs when a flip-flop enters an unstable, unpredictable state due to such timing violations. The output may not resolve to a clean 0 or 1 for several clock cycles, potentially affecting downstream logic. Here is a table listing the pros and cons of synchronous reset and asynchronous reset. There are several features to consider when using synchronous reset or asynchronous reset. For example, if you look at glitch sensitivity in the feature column, synchronous reset is less sensitive to glitches, whereas asynchronous reset is more sensitive. In some cases, waiting for a synchronous reset is unacceptable. For instance, in a medical device, the system must immediately shut down outputs on fault detection to prevent unsafe behavior. An asynchronous reset is ideal here due to its fast clock-independent response. However, metastability becomes a risk. When the asynchronous reset is deasserted, if this occurs too close to a clock edge, the receiving flip-flops may become unstable. To mitigate this, designers often use a mixed reset scheme: asynchronous assertion, fast response during emergencies; synchronous deassertion, clean and safe release of reset. Here is an example of a hybrid reset strategy. It provides asynchronous assertion and synchronous deassertion reset to the final flip-flop on the right. Here is an example of a hybrid reset strategy written in VHDL. Here is an example of a hybrid reset strategy in Verilog. Finally, I'd like to close with a reset-related note. There is another way to initialize storage elements such as flip-flops using the code shown in this slide. Although this does work on some FPGA platforms, on others it doesn't. Typically, the code is only used for simulation purposes. In actual FPGA hardware, the behavior may vary depending on the specific device and synthesis tool. For reliable operation in implemented designs, it is best to use the explicit reset logic mentioned in the previous slides. I hope this video helped you get a good understanding of the different kind of reset strategies there are in FPGA design. If it did, please like and subscribe to my channel. Thanks for watching, take care, and I'll see you in the next video.